Midterm Demo for Computer-Assisted Robotic Eating Care. Our team consists of 4 computer engineers, Queenly, Shani, Bao, and Twin.
This slide shows an overall image of our entire robotic feeding system. One of the main subsystems is the MyCobot 320 Pi robotic arm, which was provided by the Nimbus Research Lab. Inside of this, there is a Raspberry Pi 4, which controls any of the low-level motor coordination of each axis of the robot. And then the second main subsystem is the Jetson Orin Nano, which deals with all the heavier computing processing, including the computer vision and real-time updates between the time-of-flight sensor. Next, attached to the Jetson Orin Nano are 3 foot pedals, which the user can operate it by their feet. And the first button will allow the user to initiate the feed. So that will go through the whole sequence of scooping the food and going to their mouth and feeding them. The second button will be a selection button, and this will allow the user to choose between 4 sections of the plate and have a freedom of a variety of food selections. The last button will be an emergency stop button, which allows the user to stop the robotic arm at any moment if they feel uncomfortable with the movement and if they need to readjust. Connected to the Jetson Orin Nano is also the LCD, which will give the user real-time live updates of the state of the robot, whether it is in the feeding phase, whether it's in a selection phase, or whether it's emergency. It will also show the user clearly what selection they are currently on, so they aren't confused, and it will give the user any warning messages of whether the robot is connected or is disconnected, or whether the robot is in a state where it needs to get turned back on. Then there is the Raspberry Pi camera that's connected to the Jetson Orin Nano, and this allows visual intake and allows the Jetson Orin Nano to have a actual image of what the robot is looking at. And that's attached on the head of the robotic arm. And then there is also the time of flight sensor, which gives real-time updates of the depth between the arm and the user to allow for safety features. Lastly, there is the April tags, which are attached to each corner of the plate, which is separated into four sections. And these April tags allow us to calculate the coordinate locations of each section of the plate and translate that to robotic arm movement.
For our midterm demonstration, we will have the following specifications: mouth detection accuracy and effective positional accuracy for feeding to the middle of the mouth, more than 70% success rate of food acquisition onto the utensil, latency of mouth detection that is less than 10 seconds, and wireless notification delivery time.
One of our specifications involves the mouth detection accuracy, where the target was 70% of the total frames that has the mouth in it detects the mouth. When we ran the trial, we realized that the media pipe was able to detect the mouth in every frame in which it was clearly visible and didn't phantom toggle when the mouth wasn't in the frame. In the demonstration, we moved the position of the face to simulate real movement, where the user may be not in the frame and no mouth being detected. From the detection latency terminal outputs, as the frames continued, the detection times are from roughly 18.5 milliseconds to over 20 milliseconds, while the initial 10 frames were around 10 milliseconds. An important specification for our assisted robotic arm is for the spoon on the end effector of the arm to reach the user. For testing our specification on the end positional accuracy of plus minus 15 centimeters, we use the center of the mouth as well as center point of the camera video feed as the 2 target spots from which we'll obtain the difference. The logic consists of the Jetson calculating the difference between the 2 points in the x and y coordinates and sending that to the Pi for the arm to move left and y direction until both center points of the mouth and camera are matched, with a leeway or error margin of a circular radius as seen in the camera feed. We concurred that the arm was able to move to the center point of the mouth when the target mouth was moved, with ending differences of 6.5 centimeters, 3 centimeters, 3.5 centimeters for the 3 trials shown. After the 10 trials, 4.85 centimeters was the average difference, so the specification was fulfilled.
Another important specification of our project is the success rate of food acquisition on utensil. We're aiming for more than 70% success rate, and in this video, we were able to achieve 100% success rate within 10 trials. However, we do want to improve the position of our scoop right now so that it will be better at scooping without making food go on to a different section of the plate.
For the foot controlled input latency, we wanted a less than 1 second difference between when the button is released to the GUI updating. In order to test this, we took a video of us actually pressing the button and then a screen recording of the GUI updating with a timer next to it to show you the actual millisecond difference between each. And as you can see, within the 10 takes that we took, the average was 0.142, and each take was between about 0.10 to 0.20 seconds. So this is well below our specification requirement.
For the app, we test the notification and communication feature between the user and caregiver. First, we test for the meal schedule. Whenever the caregiver set a meal time, the app sends the reminder notification 1 hour before the meal starts so the caregiver can prepare the food. Next, we test for the done button and emergency button. When the user finishes eating and press done, the notification will send to the caregiver and let them know the meal is complete and they can exit with cleanup if needed. And the emergency button just send just like an alarm and let the caregiver know if something has happened. They can come and check. Also, the system update the meal history on both sides for user and caregiver. App is record the time the meal was complete and how long the meal took. We performed this test 10 times and all the notifications were deleted successfully with no noticeable delay, showing that the mobile app is reliable.
For this storyline, you can see that the foot initiation starts off the program by pressing the selection foot pedal. Then this initiates the robotic arm to look into the plate and obtain the coordinates from the able tags. Then the feed button is pressed, which triggers the arm to move to feeding the user state, where it starts aligning the spoon to the detected mouth. In the final demonstration, the selection button will be for determining the target section of the plate to scoop from, while the feed button needs to integrate the Z forward movement.
This is also the end of our presentation. Thank you so much for listening, and we're happy to answer any questions from you.